Hello and welcome to my class, PSYC 440/640. The class is called Experimental Methods, but is really more of a class on univariate data analytic techniques from a model comparisons perspective. This lecture is the second part of a lecture which originally finished up the discussion of one-way ANOVA and introduced the discussion of ANCOVA. Now, for reasons of maybe clarifying things a little bit, I broke that one lecture up into two little parts, which is what I'm trying to indicate here with the class 23.5 notation. And as you can see from the title, this lecture is just a little bit about ANCOVA, kind of getting us into the frame of mind to think about what ANCOVA is, how it works, and in the next lecture, I'll get into more detail. So, by way of an overview, today we're going to talk about ANCOVA. Well, what is ANCOVA? Well, ANCOVA is kind of like combining ANOVA and regression, which may sound a little bit silly because I've said repeatedly that ANOVA is just a special case of regression. But what I'm trying to suggest here is that we're extending the idea of ANOVA, which is normally just an analysis using categorical predictor variables, to include one or more continuous predictor variables, these being the things that we call covariates. And covariates we handle in ANCOVA in a kind of a special way. This works essentially like a hierarchical linear regression. Our covariate is entered into our first step, and the effect of that variable on the outcome variable is partialed out or removed. Then our predictor variable or variables are entered in the second step, so we can see what effect they have on the outcome variable after the effect of our covariate has been removed. What we're trying to do is reduce within group variability. This is the unexplained variability that we call the sum of squares for the augmented model, or if we're in kind of the world of regression, we call the sum of squares residual, or if we're in the world of kind of traditional ANOVA, we call the sum of squares within. It's basically what the model, that is the predictor variables that we're using, doesn't explain, the variability in the outcome variable that can't be explained or associated with group membership or whatever our predictor variable is. Now, this unexplained variability necessarily ends up in the error term of our kind of generic data equals model plus error equation. But some of this unexplained variability may be associated with a confounding variable or a nuisance variable. If we want, we can call that confound variable or that nuisance variable a covariate. And essentially what we can do is we can include that confound in our model. We can call it a covariate and kind of bring it over from where it lurks in the error term and add it into the model. Now this hopefully looks a little bit familiar to you because it's just basically the idea of hierarchical multiple regression used as a form of statistical control. It's like when we can't rely on design or methods to remove variability associated with a confound, we can sometimes use mathematical or statistical procedures to do the same thing. That's called statistical control, and ANCOVA is really just a way of doing that. If we reduce this unexplained variability, this within group variability, our test statistic necessarily gets bigger. And you can think of a test statistic, whether we're talking about an F statistic or T statistic or chi-square, as being essentially a ratio between systematic variation and unsystematic variation, or signal and noise. Remember, way back in Unit 1 I talked about this. And so if we're making the denominator of that equation smaller, necessarily the quotient is getting bigger. And large test statistics are less probable in null sampling distributions. So in a sense, it gets easier to find a significant effect if our F statistic gets bigger as compared to it staying small. So let's think about our example here. We're again using the Viagra pharmacology study from Andy Field's Discovering Statistics Using SPSS textbook. And we're imagining here that we have 30 participants. We've assigned them to different doses of the drug. Notice here that we have unequal group sizes, which you should remember from previous lectures is problematic, especially considering that the overall sample size is so small. Anyway, our predictor variable is group membership, whether a particular person is in the placebo dose group, the low dose group, or the high dose group. The outcome variable is participant libido, which again we're measuring on some sort of a scale. But there's this potential confound here, and that is partner libido. Now, presumably, hopefully, however libidinal an individual person feels isn't merely a function of the dose of drug they're taking, but also a function of how libidinal their partner is. So partner libido, if unmeasured and unincluded in our model, is a confound or a nuisance variable. It's going to tend to make the within group variability, the sum of squares within, or the sum of squares residual, or the sum of squares error for the augmented model, however you want to call it. It's going to tend to make that value larger, and consequently, it's going to make it harder for us to detect a significant effect of our main predictor variable, drug dose or group membership. We'd like to be able to statistically control for this confound by calling it a covariate. And by the way, if you have access to my Blackboard site, you can see the data there. It's a little data set. Again, if you're not enrolled in my class and if you just go to the website for Andy Field's textbook, I'm pretty sure you can download this file there for free. If you're having trouble visualizing how this looks, here's a kind of a pictographic representation. There's the total amount of variability in the outcome variable. Not everyone has the same, not every participant in our study has the same level of libido, some higher, some lower. Now we can take that overall or total variability and we can break it down into the portion that can be explained by our model and the portion that is not explained or cannot be explained by our model. When I say explained by our model, what I just mean is the amount of variability in the outcome variable that's associated with the one predictor variable that is in our model. Our model is really simple here. It's just the predictor variable of group membership. Now clearly there's some amount that's unexplained, and normally what we do is we make a test statistic by taking a ratio of the mean squared model and the mean squared residual. So we've taken those sums of squares and divided them by the appropriate degrees of freedom, but essentially what we've got there is a ratio of what we can explain over what we can't explain. And as you can imagine, and as I sort of suggested a couple slides back, the larger that denominator gets, the smaller the quotient gets, the smaller the F is. Small values for test statistics are relatively more probable in null sampling distributions than are large values for test statistics. It makes it harder to find a significant effect. What we could do, or what we like to do, is shrink that denominator term, shrink the sum of squares residual, or the sum of squares error for the augmented model, or the sum of squares error within, by pulling out some amount of it that is associated with our covariate. And by the way, you can see here in this image, I'm using that subscripting notation that is fairly common and that Andy Field uses in his textbook. Here is basically the same, well, it's not basically, it is exactly the same values, just represented with the notation that I've used somewhat more consistently this semester. So sum of squares error total is the sum of squares error in the compact model, the total amount of variability that we're trying to explain. And sum of squares error reduced is the amount that it's explained by switching from the compact to the augmented model. Sum of squares error for the augmented model is the unexplained variability, and so on and so on. Same idea, different notation. And yeah, I know that gets confusing, but it's just the case that there's different ways different textbooks will note the same quantities. Now, ANCOVA is nice. In fact, it can be really useful. It can help us detect significant effects. But like other forms of statistical control, and indeed like other forms of just statistical procedures, it depends on certain assumptions. And in the case of ANCOVA, there are two really important assumptions that we need to make. One is called the independence of covariate and treatment effects. What this means is quite simply that the effect of the covariate on the outcome variable must be independent of, must be uncorrelated with the effect of the treatment variable on the outcome variable. So to put it in the language of our example, the effect of partner libido, or covariate, on libido must not overlap or be connected to the effect of our drug treatment on libido. If there is an overlap, then removing the effect of the covariate will also remove the effect of the treatment. So we hurt ourselves about as much as we help ourselves in terms of reducing unexplained variability or within groups variability. you're having difficulty visualizing that, here's a nice pictographic representation. This comes from Andy Field's textbook. You can see in the top, there's just a kind of an example using no covariate. We have our total variability in libido, that which can be explained, that which is unexplained. If you go down to the middle portion of the figure, you can see here the ideal situation where some amount of that unexplained variability is associated with the covariate, and we can pull that away, making the remaining unexplained variability smaller, and thus our test statistic bigger. If you go all the way down to the bottom of the figure, you can see a bad situation, or a situation where we can't make where our assumption about the independence of the treatment and covariate effects is not tenable. Here, there's some amount of effect of the covariate on the outcome variable, but it overlaps with the effect of the treatment on the outcome variable. So, I'm not exactly sure how this would work in this example, but let's imagine that because of sloppy methods, your partner or the partners of each of the participants in our study are aware of the dose of drug that that the participant is getting. So, if the partner knows that his or her partner who is a participant in the study is getting a high dose of Viagra, maybe that makes him or her feel more libidinal or more sexy. So in that sense, there's an overlap, there's a correlation between however much partner libido, our covariate, affects the outcome variable, and however much drug dose, our main predictor variable, affects the outcome variable. If we were to pull out the effect of partner libido, we risk also pulling out some of the effect of the predictor variable, drug dose. So again, you can almost see this if you sort of do the visual subtraction. We sort of help ourselves, but hurt ourselves in unequal measure. So again, here's another attempt to pictographically represent this. We've got our total amount of variability. Some of it is explained by our predictor variables that make up our model, that is the augmented model. Some of it is unexplained. But if some amount of that unexplained variability overlaps with the covariate, and some amount of the explained variability also overlaps with the covariate, we shrink our sum of squares residual, or our sum of squares within groups, or our sum of squares for our augmented model, but we also shrink the sum of squares for the model. That is the sum of squares that's reduced by using the augmented model. So again, you can imagine sort of helping ourselves a little bit by shrinking SS sub r, but hurting ourselves a little bit by shrinking SS sub m. Bottom line of all of this is ANCOVA can be a useful tool for statistical control, but it's not a magic bullet. It's not something where if you don't have a significant effect for your treatment variable, your predictor variable, you can just say, well, let's find a few covariates and covary out age, covary out gender, just start willy-nilly removing covariates or removing the effects of covariates, because again, you can end up hurting your analyses as much or more than you help them. All right, well, it's a short little mini lecture, less than 15 minutes, which is amazing considering how long my lectures normally are. Hope that was a nice little taste and amuse-bouche for ANCOVA. In the next lecture, I'll be doing a lot more talking about what ANCOVA is, how it works, and how we can test that assumption, the assumption of the independence of the covariate effect and the treatment effect, and also another important assumption, which I haven't yet mentioned. Okay? Bye-bye.